It is a great pleasure to introduce you to Alexander Zhilyaev. He is a good friend and colleague of mine for I think 16, no, how many years? We calculated 12 years or so.
More or less.
We've known each other. And he's a professor at the Institute for Metal Superplasticity Problems in Ufa, in Russia. And he has, well, he's an expert in wood nanostructured materials and superplastic deformation. He has published more than 150 papers and 5 books on this area. And he has carried out his research work also in other institutions all over the world, right? And also in Canada, in McGill University, in the University of California in Davis, in the Naval Postgraduate School in Monterrey, in the University in Barcelona, Universidad Autónoma, and also in the University of Southampton. So it is a great pleasure to have him here today to give us an overview, I believe, on this topic. Wood nanostructured materials, processed by severe plastic deformation, from the fundamentals to the applications. So,
thank you very much, Stella, for nice introduction. Good afternoon, everybody. So, gonna start with that, okay? Something like that. Hablo español un poco, but I will speak English, which also I'm not very good. But anyway, Teresa told me that because of recording, I couldn't say any bad words about scientists in the world. But I was not going to say that. I was going to say good words about myself, because I'm in that age that you have to start to write memoirs. How it was going on, what you see in front of you, whatever. Apparently you like climbing up hills, and you think that you're on the peak or on the summit, and you see everything, picture it around you. But if you put eyes upper, there is bigger summit in front of you, and you have to climb. But I guess I will leave it this pleasure for you because it's much younger. So I'd like to start with some topics very general, because since 1996, when I first time came to McGill University in Montreal and brought the HPT samples, if I recall correctly, of copper and aluminum, so I can just give a talk like 20 years in superplastic deformation, like Terence Langdon giving like 25 years in ultra-fine grid materials. So, just shortly introduction about myself, which I'm not going to say bad words. I'd like to graduate from Ufa, Russia, and this is just very famous statue of local national hero Valiev, who is actually was a bandit by modern words, but now it's his hero. So you can be bandit, but in 200 years you will be hero. It doesn't matter. So this is just another statue. It's not many like you have here in Madrid, and this is some lakes, big lakes near the Ufa. And this is my alma mater, Bashkirian State University, from which I was graduated very long time ago, 1981. So this is our building of Institute of Superplasticity. It's only one institute in the world with such name. Supposedly it should make research only in superplastic behavior, but unfortunately there is a little research nowadays doing in superplasticity. And this is just, I'm going very quickly just to stop more important stuff. It's very quickly, it's Montreal, Canada, it's new building where I stayed last 1998. We published quite a nice paper in CSL lattice in monoclinic zirconia, quite interesting, with Valiev RZ, who is now in Canada. Recently he visited us, and just we met after many years. And he's just missing, because now he's engineer and he's missing research a lot. So, and some results, and this is just quite interesting because it's first time we did in my research high resolution TM, and this is just, it's not seen clearly. This is just broken the boundary, and with some imagination, you can say that this is end of this boundary can be disclination, which was very popular, very famous at that time, and there was no experimental evidence for the observation of disclination. So we claim it could be some disclination. So, oops. And this is University of California in Davis, California, of course. It was a farm in 1910, I guess, in University of California, and then transformed it to the separate campus, and there is a huge department of chemistry and material science, which is now quite famous for this material science research with Professor Mukherjee, and they, here we first time made some work on the nanocrystalline materials I brought from the McGill University in nanonickel electrodeposit, and we published paper, very nice paper, on the superplastic behavior. And since that time, it's already 17 years, there is no clear explanation why it happens. There is controversial explanation by Professor Mukherjee's son McFadden, which I couldn't agree, and there is this behavior was repeated by Chokshi, and still no clear mechanism for to explain the superplastic behavior. So this is just a picture from this electrodeposit nickel. You see, we got almost 900% at 420 degrees C. It was world record that time for pure metals. Remember, it's pure metals. For pure metals, because usually people say it's impossible during grain growth to obtain superplastic behavior in pure metals. So this is Spain. This might be last Spain because I'm here third time. First time it was at Terra near Barcelona, the University Autónoma de Barcelona, and I lived in Cerdanyola, very nice small village. So we did some work, and especially with this experimental parameters influence green refinement, published in ACTA 2003, which got more than 500 citations now. So this is a research paper, not a review, because review is getting citation much easier. And some work done with Hungarian postdoc Adam on the in situ crystallization during HPT in metallic glasses, aluminum-based metallic glasses. And we did also cold compaction metallic ceramic ferromagnetic, anti-ferromagnetic by high pressure. This is just quite interesting now because it was first time for cold consolidation with very high strength material. And this is just beautiful, beautiful paradise. It's Monterey in California. It's among the 5 places in the world where the weather conditions, humidity, temperature, air pressure is the best for retirement guys. The best. If you get enough money and you get retired, you have to go there and live the rest of life. Professor McNally learned that, and one of the places was in former Soviet Union Republic, Kyrgyzstan, near the Issyk Lake, and he said, "Oh, Alex, can I go there just to live there after retirement?" I told him, "Terry, you're living in this place. Why you should change it? It's just wild area." So we published quite good papers there, very, very strong, and we actually did on the stir zone friction stir welding material bronze, like we did miniature samples to measure the mechanical properties. Actually, it was measured by mapping microharness, And it's, of course, it's consistent with micro-hardness mapping, but it just trivial tensile properties. So this is CNIM, it's in Madrid, you know where it is. And actually, also during this stay I published quite nice paper, including with Teresa. So actually, I like this work because it's high pressure phases in zirconium alloys. It's actually still actual and continuing intrigue people. And also we published with Adam Rivers and Tony Spatov on the hydrogen storage in ball milled and ball milled HPT consolidated magnesium alloys. And you see that there is some difference between ball mill, which is broken line, and solid line, that you can put more hydrogen inside, and it's actually in form of not powder, in form of tablets, consolidated, very porous. And also in 2011, 2014, I've been staying with Terry Langdon in Southampton University, which is, you see that red bricks. You know, there is three types of the university in UK. White stones, red bricks, and glasses university. And they divide it like white stones, it's Oxford, Cambridge, which built from the white stones, very old, and they consider themselves only as a real university in UK. This is new one in red bricks, which was started at the beginning last century. And of course, beton and glass, it's just brand new, which is just like teenagers, and they're not considered as a real one. So there is a very huge competition. But in getting grants from industrial red bricks, they have their own association, called like similar like Red Bricks University of UK, and they got more money than the fundamental White Stones University for industrial research. So now it's just quite good in the top of 10 universities in UK. A lot of foreigners. There is no space to teach foreigners because there is a huge line before gates. Because there is strong rules in UK. You have to give a postgrad student the place, you have to give a computer, and he has to learn and study during the 4 years. So in this we did quite nice work with Megumi Kawasaki, who was a PhD student of Terry Langdon. Now she is a prof in Korea, in Seoul. So we put just like 3 samples, aluminium 1050, the ZK60 between them, and compress it and just make a 5 rotation, and we got some increasing at the age, and after 1 and after 5 we got intermetallics at the end. Actually, at room temperature, by placing 3 pure actually metals, we got intermetallics. I guess it's happened not very often, and usually it happens during accumulative roll bonding at higher temperature, 450, something like that. And finally, I got again here. This is I'm just formally with CTM and working with Professor Jose Maria Cabrera and UPC, doing some work on superplastic deformation. So of course, I could present new results, which is quite exciting about the wear resistance and electroconductivity in copper chromium zirconium alloy, where actually we published recently a paper that's saying that BKS model is describing quite effectively the strengthening in this material. Also, we have done some work, new one, not published, in ultrasonic treatment of nickel processed by ECAP and by HPT. Quite intriguing results, because depending on the amplitude, you can get following, I mean, further the hardening of materials or softening. It's quite interesting, and also some work on other materials. But I guess some of you not very familiar with high pressure torsion, and I just go through the principles of high pressure torsion very quickly. And then the most interesting part will be there if you have enough patience for this. So this is just three types of HPT sets, like constrained, unconstrained, and this one is flow, free flow to both sides, constrained A and constrained B, which called by Terry Langdon semi-constrained like this and constrained like that. It doesn't matter actually. And in this case, you will get very thin samples like 0.1 millimeter, and not very suitable for the tensile properties. In this case, both cases, you will get more thicker, like 0.8 millimeters in thickness, that you can cut some miniature samples, micro samples, to test tensile properties. This is strain calculation. It's very rough based on the geometrical approach. Probably it's not very correct, but anyway, some people using this one, calculating equivalent strain by von Mises equation, which is actually was developed for the very small strain, not suitable for the large strain. And this is just like setup, which it was firstly designed in UFA in a lab of Valiev, who is my colleague, and he was a supervisor of my PhD work. So, and this is some metals and some achievable properties. So it's quite famous, you can find it. So, and FCC materials, like, because of HPT and strain depending on the radius, in the center actually, by geometrical consideration, there is a gap, a zero. But measuring the properties through the disk, you can discover that there is strain hardening in the center as well. So it was just unexplained stuff, but this is work done, published in 2003 in Active Material. And before that, everything published on HPT, the paper was saying after 5 turns and under pressure 5 gigapascal, you can get homogeneous distribution of hardness across the disk. But we did very careful examination and found that still there is some profile of micro hardness even at a pressure of 5 gigapascal and after rotation 5 turns. So depending on the number of rotation and load. So still there is some gap. You see there is still gap. Not small one. It's in range of the error, but you can detect it. So this is a microstructure. I will not stay. And this is just also first time using EBSD to characterize nickel in the HPT nickel, showing that there is a microstructure at the edge, at the center and at the edge. So you see quite similar microstructure, and methylation distribution function also similar, but if you look carefully, there is some slight difference between them. So when we check with aluminum 1050, we found that after n equal 1, the homogeneity will improve significantly after rotation, or at 6, it will be just straight line in error. It's the same, and this guy, Yuri Estrin and Dimmatt-CM with co-authors make a calculation, and they show that with model of straining you can just predict that the gap in the center will disappear with a number of turns. So at the same time, in commercially pure aluminum, we discovered with Terry that sometimes is grain size near the edge is bigger than in the center. It's controversial stuff because strain in the edge much higher than in the center. And Terry was smart enough just to repeat this material, this experimental work for the high purity aluminum, and found that this is just actually recrystallization take place during room temperature high pressure torsion of the aluminum. So that depending on the purity of materials, you can get or strain hardening or just recovering or just even recrystallization. So this is some work done on copper, and this is quite interesting work done on the rapid quenching nickel. If you put the melt of nickel on the disc of copper, rotating with very high speed, so you will get some stuff, the ribbons, which have a quite big grain size. If you consolidate these ribbons with HPT, you will get further refinement, which is smaller than that one, and but unfortunately we plan to at least to repeat our results for electrodeposit nickel. But it's still mystery. We don't get any superplastic properties for these materials. Why? I don't know. If somebody knows, it would be great. So this is just kind of work done on copper. A lot of stuff. I hope it not boring, but I promise you to talk about application, of course. And this is just, I would say, just HPT is not industrial process, definitely. Even now, I know that some industrial application for, I would say, quasi HPT. I did show it today. But that one, that setup is not for industrial use, but it's excellent model process for refinement almost any materials, if you can get the proper angles, and to consolidate powder of metals and alloys. But still there is some practical application, kind of biomedical parts, titanium, zirconium, nitinol, because if you know some stems or screws, whatever, it's so tiny that can be done from the HPT disc. The magnetic materials, which can be done in shape of tablets, because in that case, maybe you don't need to consolidate powders to 100 density. It's the same for materials for hydrogen storage. Usually in hydrogen media, it's in powder shape, which is inside of some cylinder supporting this powder. And there is one problem after cycling, the powder starts to compact and it's a decrease in its properties. If you do cold consolidation, that it will be like again in shape of tablets with some porosity, but it will be stronger with mechanical point of view. High temperature superconductive materials as well. There is a lot of investigation of that. Structural application, miniature device platform. This is just what I learned. So that nickel is actually base metal for the chip. So on the nickel you put some silicon, then some transistor, whatever, 100 millions. And it's when you get smaller in this transistor or whatever, put more stuff here, it's heating stronger. So it's just heating, cooling, it's just like thermocycling. So then it's a problem when you put the coarse-grained nickel, it will be anisotropy in different direction. During this thermocycling, because it's increase extent in different direction with different size, it can broken this on the top of that one. So you can use a ultra-fine grain nickel or nanocrystalline nickel just to make it homogeneous, that it will just extend in different directions with the same value. And just for welding, just if I show you, as I show you, just you put two different materials to HPT, and they actually welded with creation of intermetallic properties. So you can find more in this very nice, I like it, very nice review, which was crafted with Ishat Sabirov, is here. And is in a recent book which published in Wiley Sons, also the quite thick book, I will show you. And this is my collaborators. So the staff, there is two collaborators here in this auditorium. And this is what I published, something in these books and something stuff. You think it's the end, but it's not the end. This is just the start. This was about me. Now about some funny speculation on HPT nickel. Because in METS, in the last nano-SPD, we had big discussion with John Jonas, who was supported by many people in the staff, how to calculate the equivalent strain in HPT. Of course, any calculation is incorrect because it's developed for the small actual strain comparing to HPT. But anyway, when we calculate equivalent strain, you have to think, if you calculate equivalent strain in von Mises stuff, that means you put so huge strain in the material, when you multiply with stress applied, you will get so huge energy you induce to the material. When you calculate this value, it's incredible. Let's see. So this is physical data. This is just steel edge 13, usually used for the anneals. This is the instrumental steel, which is density, specific heat capacity, thermoconductivity. This is temperature diffusion, thermal diffusivity, all this mixing, Russian and stuff. This is just weight of these anneals. Imagine, it's almost 1 kilo. This two stuff, 1 kilo. This is anneals. This is nickel, which is very close to density in specific thermocapacity and so on and so forth. It's smaller stuff. But look at this. It's 3 orders of magnitude, 4 orders of magnitude less. And I don't think some of you just ever experienced to touch these anvils after HPT. They are not extremely hot, but they are warm, very warm. So that means there is some energy going to the heat. So this is just set up. This is what it's. This is thermocouple. It's 7 millimeters from the. This is schematic, of course, and this is just measuring the temperature during the HPT process. If you record it, then this is time or number of revolutions, because it's 1 revolution per minute. For different materials, you see, of course, aluminium, the smaller increase in temperature. This is copper, this is nickel, the highest. And this is for HCP, some HCP materials. Same softer, of course, there is no like aluminium. And these two guys are almost similar. This is published in the proceedings of nano-SPD 6 conference. Let's calculate the heat released in anvils during the process. It's very easy. This is per unit volume. This is just density, heat capacity, specific heat capacity different than temperature. You see the different temperature for 6, like 25 degrees, for 10 it's 35 degrees. So just very simple calculation gives you quite big amount, 90 megajoule per cubic meter. It's huge amount, but remember, cubic meter is huge stuff, but it's just for unit volume. Then we have some data on nickel, HPT nickel taken from the PhD thesis of Elena Kornikova, which he got in 2001 in UFA. This is just measuring strain, and this is stress, and you see that it's close to 1000 megapascal, which is 1 gigapascal, which very close to value you can estimate from the microharness test, which is Vickers measurement gives you 3 gigapascal divided by 3, it's 1 gigapascal, more or less similar. Then, if you measure vacancy concentration versus shear strain, you see you can get up to 10 minus 5, huge amount of the vacancy, and Professor Zhilyaev claiming that all of these vacancy actually responsible for this unusual properties of HPT materials, and also dislocation density very high. It's like higher than closer to the 8, 10 to the plus 15 square reciprocal meter square. So we can use all this data to evaluate how much contribution of the energy could be from vacancies. It's quite easy. This is just everything just calculated. It gives our 2.3 megajoule cubic meter, divided by cubic meter. About the dislocation, we can calculate this like this. Sorry, this is just some shifting, but by this equation, which gives 16.5 millijoule per cubic meter. And from the grain boundaries, it can be evaluated by specific surface energy of Heimel boundaries, which is about 1 joule per square meter. And we calculate the total surface area per cubic meter like this one. It gives by the highest value, it's just normal. This is just it's very suitable. And if we calculate everything, heating gives 90, and all defects gives like 76. All the case gives you 160 megajoule per cubic meter. Okay, this is good or bad? I don't know. But if we take the stuff and calculate the plastic strain putting by shear strains, and shear strain, and we take like two stuff like this, it gives like 2 megajoule per cubic meter for n equals 6. If we divide it by time, which is 360 seconds, we will get capacity 5 gigawatts, 55 gigawatts, which is comparable with the capacity of renewable energy in Spain in 2015. So, it's impossible. That means this calculation using the von Mises strain is incorrect. Using Henry definition of current strain, I got evaluation like 173 megajoule per cubic, which is quite close to this value. So it's possible. I am not sure, frankly speaking, not sure in my estimation, but the number we get quite close. But the most intriguing stuff is that the heat release is half of the plastic strain energy. Usually, in any calculation, people guess that heat release 0.9 of plastic strain. And it caused me problem when I estimate minimum grain size can be attained during HPT because when I take 0.9 strain plastic energy goes to heating, it was not enough energy for me to refine the materials, and I was getting the recrystallization. So that means from this calculation, I can guess that half to half of plastic energy going to the heating and going to for the refinement of the materials. So finally, this is the end, and it was 40 minutes. Okay, I have been so fast, so I could slower. Thank you. So, if you have questions, I can.
Any questions for Alex?
I got a question. So when you do your high pressure torsion, what's your limitation on your sample size?
It's depending on anvils and depending on condition, because to need torsion, you need sticking condition. So you need high pressure to make enough sticking condition to not to have slipping. So that means smaller size, you will get better condition. Usually people use 10 millimeters in diameter and 1 millimeter in thickness. But you can get smaller one. It's very old stuff, so-called diamond anvil cells, when they use 3 millimeter diameter diamond anvils and just micrometers of thickness in samples. But in that stuff, it's very small one. HPT big one, but it's small one, you can get 100 gigapascal in pressure. So that diamond anvil cells was used for the study materials under extreme compression.
Do you need a special setup for the small one?
For the smaller one?
Yeah.
No, it's commercially available. It's just like on the table stuff. But for the HPT, if you see that, it's quite a big one. What do we do? Oh, here. This is quite big.
But that's 10 millimeters.
Yeah, 10 millimeters.
So you said this couldn't be used for bulk processing. Can you stack up parts?
You mean you can stack up, but as you get thicker, you break the sticking condition. All of them will be sliding. They just go down. Problem for the compression as well. There is a ratio between thickness and the diameter, actually surface area, when you can get sticking condition or sliding
But
condition.
some people have done two on top of each other. Have you done two pieces on top of each other?
Yeah, this is what we did, three pieces, actually, you probably missed the point. But all of them was, no, sorry. Before HPTA. Yeah, here, three pieces. It's aluminum and magnesium between them. All of them was like about 1 millimeter in thickness. But when you smash it, they will be like some of stuff will flow out, and they will be final thickness about 1 millimeter as well.
Any more questions? You had measured the temperature, the increasing temperature of the ambits.
Yeah.
But
Actually, the temperature of that thermocouple.
yeah, with the thermocouple. But it's possible to know the increasing temperature of the sample?
It's a difficult question, depending on the. There is people do that very easily, because if you have very simple software to solve this equation, and it's quite easily for this geometry. because you can consider it an infinitive semi-infinite plane. But the problem is, with solution of this equation will much depend on the boundary condition between disk and envelopes. Many people say, like, when you have 6 gigapascal compression, the contact's so tight that there is no any difference. But there is difference, because if you look at this stuff, it's thermal diffusivity. You see, even everything almost the same because of this guy. This guy is also even higher. I mean, it's the same actually. So there is a drop in the temperature between the samples and envelopes. If it drops, like decreasing the heat transfer to the envelopes, that means samples will be heated up, and the recrystal or recovery, at least recovery process will take place. How to control it, I don't know. Probably it's possible, but even some darkness on the surface will change drastically your boundary condition. You have to make sure that everything identical to make a set of experimental work and measure the temperature to say, okay, I know what is stuff. Actually, one of the ways just to put thermocouple inside of the material and broke it.
Yeah.
I told the, what is this guy, Iranian guy with Harita? Edalati. I told Edalati. But he didn't follow me. I told him just take it to aluminum disc, clamp it with a thermocouple, and then rotate it. He did a little bit different. He put on the top surface, and then on the disc, and then press it and rotate it. Of course, thermocouple was broken after like half of rotation or something, but he didn't see any changes in temperature comparing to the thermocouple. Definitely, I also made some experimental work. I put thermocouple here on the side of the angles, comparing to this thermocouple. It was like 2-3 degrees difference because of the cooling from the side. So far, I have no answer what's going on there.
Also, between the clamps, there is any lubricant or something, because I guess most of the heat comes from.
Yeah. So when I came first to the Langdon lab, they have very strict procedure to do samples. They put some lubricants here to make sure that it will be sliding, just to make easy. But remembering from the Rima Lapovok talk, she told me when I put lubricant for ECAP, even they put it all times, the lubricant smashed away during the first pass, just immediately. And you have luminal surface, just free surface. And the same actually happened with this stuff. Remember, this is 6 gigapascal. You put lubricant here. When you compress it, lubricant just flow out on that one. Almost there is no lubricant. And then finally, at the last year of my stay, they told, okay, we shouldn't use the lubricant because it makes definitely dirty samples, and just you cannot control sometimes it going to inside to cover the surface of the sample disc, and then you have no idea what is the condition for that sliding for sticking. Probably because it's closed surface, there is nowhere to flow out. It may create some thin layer for sliding. But actually, we checked in this paper. If you look, I did some samples with lubricant and without lubricant, and measured the temperature increase. Absolutely identical. Absolutely identical.
Any more questions? If not, let's
Okay, thank you very much
Again.
for your